Swayam Prabha. Digital India. Educated India.
So this application example is an indeterminate structure which is subjected to an internal torque, as you can see in the figure over here. So you have this shaft over here, A to B, part of it which is solid and part of which is hollow. So maybe we just go ahead and mark that. So this is the solid part and this is the hollow part, right? And where you're having at the exactly at the center between this length of 125 at the center of this member, you have a torque of 120 Newton meters. So the question asks that to find the support reactions, you are given the diameter of the solid core, which is 25 mm, and the hollow core has an inner diameter of 15 and an outer diameter of 25 that you have over here. Okay. So for this one, first let's go ahead and so we are trying to find the support reactions. First, let's go ahead and draw the free body diagram for this entire member that is there. So if I have to represent the member, maybe something like this over here, where this is my end A and this is my end B, and say the point at the center where my torque is being applied is this. So let me call this point as C, right? So C is somewhere here in between. C is here. Now at this particular point C, you have this torque of 120 Newton meters that is being applied. Now follow your right hand rule, that where the direction towards where the arrow of the moment points, that will your thumb will point towards the direction where you should mark the double arrow for the torque. So in this particular case it points towards B. So let's just go ahead and mark the torque here, that is represented by these double arrows, remember. So this is the applied torque T, which is 120 Newton meters. Now as a consequence of this applied torque, you will have the reaction torques at the ends A and at the end B, and let me just mark these reaction torques as something like this. This is my reaction torque TA, and at the end B also I have the reaction torque TB. So the basic relationship from equilibrium, some torque equilibrium relationship, I can write it out as my TA plus TB is equals to the applied torque T. So that is one relationship that I have over here. So let me maybe mark this as relationship number 1. Now, how do I find TA and TB? So that's the question. That is the support reaction. So the question asks you that how do you compute your TA and TB over here? So what is the equation of compatibility which we are going to use? You can see that the end A and the B, they're clamped, so they are not going anywhere. So your overall, the phi that you have, the angle of twist between A to B is going to be 0. Right, but you may have the internal phis, your C, the point C over here may move, but if you say draw a straight line from A to B, that straight line does not move anywhere. So the overall phi for that entire structure, phi AB, is equals to 0. Now, so how do we compute this? So the phi AB, if we have to just write it out, that we have our phi from A to B is equals to the phi AC. This is again, in drawing analogies with your axial loading, the total delta equals delta 1 plus delta 2 and so on, and it depends what the final delta is. If you have a clamped support with an axial load, that is 0. Here for the torsion case also, if you have a clamped ends, then the total rotation is equals to 0. This is phi AC plus phi CB over here. Now, how do we compute phi AC? Phi AC is for this point, and phi CB is for this portion of the shaft over here. Now, as you can see that we always draw the sections where we have the discontinuity. So from here to here, so I have an applied torque at the point C. So I am going to go and take a section, maybe section 1 over here and a section 2 over here. So maybe if I have to show in this 2D diagram, this is 1 and maybe this is 2. Now for the first portion, so for the AC part, so if I have to draw the free body diagram there, how do I, so along where I cut the section, how do I represent that? So I represent that as, I represent that as something like this, where at the left end, as you can see, I have my reaction torque TA, and at this particular end I must have an internal torque. So let's just write that T internal, which is going to be equal and opposite to sorry, this is not a reaction. The internal torque must be equal and opposite to the torque TA that you have over here, simply from equilibrium, right? Now these two torques are pointing outwards, these are pointing away from this particular shaft. Now let's look at this guy over here at this. So this is for section 1. This is what I drew over here, is for that one between A to C. So this is from A to C, right? Now for the part B to C, if I draw the section from here to here that I have, right? So for that, what I get is that at the right end I have my reaction torque, which is TB. So at the where I am cutting this section over here, which is this point, at this particular point I am also going to have an internal torque here. So this internal torque in this particular case is going to be equal and opposite to TB here, right? So this is for my section 2. Now for the part AC, how can I write my phi AC? We know that, so I am just going to split these two guys over here, like this one and this one, and write the individual equations for both. So what I get as my phi AC, remember the torsion formula, phi equals to TL divided by J times G. So phi AC will be equals to the T internal in the section AC times L of AC divided by J of AC times G, right? Let's say it's made of the same material, so G is the same for both the AC and the CB over there. Okay, so that brings you, because T internal in the portion AC is nothing but equals to this A over here, because this is for the section AC. So that is equals to TA times LAC divided by JAC times G. Okay, so that gives you my phi AC over here. Now the next one is my phi CB. So let's go ahead and write that as well. Phi CB comes out as equal to T internal CB times length of CB divided by JCB times G. Now here is an important point to note. Look at the direction of previously what we had. TA was pointing outwards, whereas your TB and T internal B, that is T internal in this can be, is pointing inwards. Now as is customary, that remember for the axial loading also what we had, that when it was the forces were pointing outwards, the tension was positive, inwards it was negative. For when we mark torques as well, when you have the torques which are pointing outwards, then you typically mark them as positive. If it's pointing inwards, the torque and the corresponding phi becomes negative. It is analogically similar to tensile and compressive. So here this is going to be minus of TB. So here I should write a minus right here as well. Minus of TB times LCB divided by JCB times G. Okay, so I have written down what are the internal torques that we have over here. So now I'm going to have to use this compatibility, because I know my phi AB from here to here is equals to 0. So that means if I take that condition over here, so that what I get, my phi AC plus P of CB is equals to 0. So that gives you the relationship that TA, so that means TA times LAC divided by JAC times G plus of minus TB times LCB divided by JCB times G is equals to 0. Okay? Now here this is an interesting problem where the shear modulus doesn't matter, because if it's made of the same material over here, this G goes to 0 over here. So this G, if you take it on the right hand side, that becomes equals to 0. Now also one more thing to note over here, that for this problem your length of AC and length of CB is the same. So this LAC I can replace by L, and this I can replace by L, where LAC equals to LCB equals to L, right? And this also goes to 0 because this is a common parameter that you have in between, you know, these two terms of on the left hand side. So this further simplifies your expression, that TA divided by J of AC plus of minus TB divided by J of CB equals to 0. Now this is one more relationship that you got over here. So this is your relationship number 2. You have one relationship 1 over here. Now here you need to calculate what is going to be your JAC and what is going to be your JCB, because JAC, remember, it's a solid core and JCB is a hollow core that we have. So now if you go ahead and compute the JAC, so the JAC for this part, this guy over here is going to be pi over 2, and the diameter of this one is given as 25. So it's going to be 25 by 2 raised to 4, whereas your JCB here is the hollow core. So this is that hollow part which has an internal diameter of 15 and the outer diameter of 25. So JCB is going to be pi over 2, 25 by 2 raised to 4 minus 15 by 2 raised to 4. So once you have these and then you use the relationship, this one and this equation over here, you have two equations and two unknowns. So I will not go ahead and, you know, punch in the numbers and solve it. Please go ahead and solve it. I will give you the final answer that you will get after you solve these two equations and find out the two unknowns, which are the two reactions that we were supposed to find. Remember, this TA and the TB. So your equations are in terms of the unknowns itself. So what you will get as the final answer is your TA will come out as 64 Newton meter and your TB will come out as 56 Newton. Okay. So I hope this overall problem was clear for this indeterminate shaft. So you had a indeterminate structure with a torque at the center. We used the equation of compatibility to find out the reaction torques.
We are slowly reaching the last bits of our topic on torsion, and I'm not going to let you go without the last spark of amazement. What we are going to discuss in this topic are essentially torsion of thin-walled members, and we will learn a very important concept there on the shear flow. Then we are going to move ahead and we are going to talk about stress concentrations in an exactly similar way we talked about the stress concentration in the axial loading case, where you have, you know, sudden discontinuities, how the stresses peak up in those regions. Lastly, I'm going to leave you with some future reading material. If you're interested, you can, you know, take a look into that one. So let's go ahead and dive in on our very first topic, that is the torsion of the thin-walled members. Now, before we go into the torsion of the thin-walled sections or the thin-walled tubes, what I want you to do is that I want you to first recollect what we have studied. Right. So now if you see, suppose you have a shaft, right? So let me maybe draw the shaft over here, where, say, in this shaft, say the shaft has a cross section. If I take a look at the cross section, suppose it is a circular cross section. So this is, say, this cross section over here. It is a circle, nice and round, and here I am coming and I'm applying to the shaft, I am applying, say, a torque, right, equal and opposite torque. So it's a balanced system, right? Now what we have studied until now are these solid shafts, right? Solid circular shafts. The circular is more important. Now if on this circle that you see, if I take 2 points, say this is the center of my circle, somewhere around here, and if I take any 2 points on the circumference, let me maybe pick a point B over here and pick maybe another point C over here, both of which are of course equidistant from the centroid with the radius say R. What we have learned is that since each of these points are at the same distance R from the center, I am going to have my tau, that is the shear stress at B, must be equal to my tau at C, 2 points at the extreme periphery, right? Now this is true because your R at B is equals to the R at C, which is equals to the radius of the circle. As opposed to this, let's consider another shaft, prismatic. Remember, mind you, it's prismatic. It is prismatic in the sense, and if you recall our discussion on prismatic sections, it has the same cross section throughout, right? And suppose that particular cross section, which is same throughout, is now this one. It is not a circle, it's a non-uniform cross section, but it is same throughout, right? So it is prismatic in that sense, but the cross section itself is not a regular circle, not a regular rectangle, maybe, you know, a kind of an odd shape, something like this that you have over here. Now if for this shaft that I am looking at right now, if I am applying torque, balancing torque at both the ends, say T over here and T over here as well, and if I take another set of 2 points, let's say point B and another point C over here, and for this irregular cross section, let's say my centroid is somewhere over here, right? Now for this shaft, which has a non-symmetric, you know, it's a non-circular section, and let's say the points, the distance of the points from the centroid, let me just mark them, are RB and RC, which is of course different than the R that you had previously, and they're not equal. So in this case, my tau B will not be equal to my tau C. Why? Since my RB is not equal to my RC, right? So let's have this concept first ingrained in our memory, that if I am looking at a section which is non-circular, although if I'm applying equal and opposite torques, if I take 2 points on the circumference which are not equidistant from the centroid anymore, they have 2 different distances RB and RC, the shear stresses which are developing as a result of the applied torque at both the ends are not going to be equal, right? Now once we understand this, let's go to some interesting discussions on thin-walled tubes, right? So for the thin-walled tubes, I'm going to present to you this figure over here. Okay? So let's try to understand the figure, and then we will go into the derivation and discussion on a particularly important item, that is the shear flow. So what you have is a thin-walled tube, something like this. A practical example of this may be something like this. You have a thin-walled tube and it's non-circular, right? So if you take a look at this cross section over here, it is not a circular cross section. I sort of, you know, bent it over here. So it is a non-circular cross section that you're looking at. Okay? Now in this thin-walled tube that you have over here, suppose you take at, you know, in somewhere from the left end to the right end, if you're taking a small element of thickness dx, and you are isolating this element over here, that is A, B, C, D, and you are essentially taking out this entire, you know, cross-sectional segment, and if you are portraying it over here, and you're assuming the wall is thin, that means that your shear stresses across this thickness over here, remember when we're looking at the solid shaft, the shear stress is maximum at the exterior and minimum at the particular centroid point that we have, right? So in this particular case, if we are looking at the shear stresses, how does that look like? If I'm looking at the shear stresses, it is something like this over here, right? So since this is a thin wall, right, it's a very thin, and say the T varies, right? If the T varies, and suppose here my thickness is say TB, and at this particular point my thickness is TC. And as we learned from our discussions in the couple of pages before, since this is a non-circular cross section, my points B and C are at two different distances from the centroid. So here I am going to have a particular shear stress tau B. Here I will have a particular shear stress tau C over here, right? And in between I will have the transition, because remember this tau B that you see over here is actually the same across the line. So if you go ahead and if you draw, say if I go ahead and draw say one line over here, all across that line, all across this line I'm going to have tau B. Similarly, all across this bottom line, if I am going and drawing this one, I am going to have the tau C. So in between you must have the transition from tau B to tau C. So it's tau B over here, and exactly at that interface you'll have a tau B as well. Remember, if you take even a smaller element over here, your shears must balance out. And as we made this assumption, since the wall is thin, this tau B stays the same throughout this thickness. If you remember, it was a solid one, then at the centroid you will have a 0, at the exterior point you will have the tau B. But if the wall is very, very thin, as in this particular example, if you have the wall which is very, very thin, the shear force on this outer periphery, tau B, and this small thickness that you have, it can assume to be the same. So in the internal and the exterior you have the tau B over here, right? So now that I have that this TB and TC and this tau, now if I am doing the force balance, if I do the force balance on this one, if I take a look at this element over here, the same element, all I have done, instead of representing at the shear, I cannot balance the stresses, I can only balance the forces, right? The equations of equilibrium are applied to forces, not the shear. So if I take this one, and remember it is the same thickness that we wrote down, that this is the TB and this is the TC that you have, which is exactly as you're looking at over here at this particular point, this TB, TB, TC, TC over here. So how do I write this force FB? I can write this force FB as, let me try to write that down. My force FB must be equal to, force is stress times the area. So here the stress is tau B times the area will be TB and this length dx, right? So this small rectangular, thin strip kind of an area. The area is TB times dx. So the force is going to be, FB will be tau B times T at B times dx, right? Similarly, for the bottom part, FC, I can go ahead and write FC as, it will be tau C times thickness there times dx. Now, although I have written out these forces, I must satisfy equilibrium. My total FB, which is in the horizontal direction along the x direction, must be equal to the FC. So if I go ahead and write that, so from my summation of fx equals to 0, which is always valid, what I can write from these two equations 1 and 2, my tau B times TB times dx must be equals to tau C times TC times dx, right? So here my dx and dx goes for a toss. So eventually I end up with a relationship that is my tau B times TB is equal to tau C times TC. Now what does this expression tell you? I had taken two random points, B and C, or this a quadrilateral element A, B, C, D, and what I'm seeing is that the product of the shear at B times the thickness at B is equal to the product of the shear at C times the thickness at C, right? So if you consider this, all along these points B and C could have been anywhere. So all along this thin walled tube, all across the cross section of this thin walled tube that is there, the product of the shear and the corresponding thickness, remember this T varies, so I had a different thickness here and a different thickness here, I had a different shear here, I had a different shear here as well, but the product of the shear and the thickness at that particular point remains a constant. This particular guy can be approximated or can be said as a variable Q, right? With this Q that remains constant across this entire cross section, and this Q is known as shear flow. So this is very important. So let's just make it a marker over here. This Q that I just wrote over here, this is known as shear flow, right? This is an extremely important concept, and later you will see we will study this a little bit more in details when we talk about shear stresses in beams and so on. So the overall conclusion is that, let's just maybe write it down, that as long as the thickness is small, product of tau and T is a constant, and this constant is nothing but our shear flow. It's a very interesting concept which you will see later you will make a lot of use, right?